Very good. Thank you. Well, being here after Sami is quite intimidating, I have to say. I share with him the interest in physics, and I'm looking at computing from other angle at this moment. I got interested in a lot, significantly in relationship between energy and computing. And I do relate a lot with what Sami did. So we're continuing on that route, on that direction, by using EMFI, EM, in order to glitch, let's say, a device, and to gain the highest privileges on actually the Google Wi-Fi Pro, so not a device, but that device. We are going to get EL3, and we will be combining a few things, and I hope that you find them interesting. So the goal of this talk are to discuss how we got the highest privileges, the EL3. EL3 is basically the highest privileges on the device in a ARM trust zone based or an EL3vated based device, which is the case for the largest majority of devices nowadays. Basically, we are going to do this on the Google Nest Wi-Fi Pro. We are also going to discuss EMFI characterization of a Qualcomm SoC, which is at the base of the Google Nest, which is the IPQ5018. We show how Wi-Fi fault injection can complement software exploitation, and this is one of the few examples where fault injection is actually used for attacking a trusted execution environment at EE. There are examples out there. Some are academic, but in the hacking community there are really not that many. So, for us, we are going through the introduction. We are going to how to get to EMFI. We're going to see what is needed, basically. This will require bypassing secure boot on the device first and obtaining root privileges, which would be a talk by itself already. Actually, it's been already done. And building the fault injection setup. We are going to characterize our target, our SoC, system on chip. And then from there, from what we obtain, we go to EL3. To the highest privileges. Let's do this together. So basically, it's Cristofaro and Nick. We work together at Realize, and we both did this research together. I'm the one presenting here, but refer also to Nick when you encounter him, basically. In 2021, we broke the IPQ4018-19 SoC. This was a research which has been published. We broke this with software vulnerabilities in the TE, and this has been reported to Qualcomm as well. This affected a number of products, including some notable manufacturer over here. This has been fixed, but we also took the liberty to use EMFI, which to use a fault injection to break the TE. But I mean, that was a kind of an exercise. Nowadays we are doing a little bit more at this moment. So today we are continuing the trend of attacking that IPQ SoC, which is the next family and generation. Now is the IPQ5018, which is the basis of the Google Nest Wi-Fi Pro. It supports secure boot, of course, in trusted execution environment, TE, which is ARM trust zone based. There are TEs which are not trust zone based, and the environment is QSE, Qualcomm Secure Execution Environment. Our target as a basically a recent firmware version is not the latest one, because we started doing this research during 2024 for obvious reason, and we are reporting this just for the sake of being precise in our recounting. The RE sides, the non-secure sides. So what we usually see is basically U-boot, people the bootloader, and the OS is basically Android based on Linux kernel version 5.4. There is a nice hardware review provided by Sergey, which is at the end of the room, by the way, exactly at hardwear.io in the Netherlands in 2024. It's nice to quote you, Sergey. Very, very been useful. And in this case, this shows a little bit of the boot process. Now, while this can seem complex, you just need to watch on your left. On the left, there is the boot process for the application processor. You will see that there is ROM code, number one. Then there is number two, the SBL, and they both run at highest privilege, which is EL3, which is always secure and the highest one. Then the SBL will execute will initialize QSE on the secure side, on EL1, running at secure EL1, or actually secure at EL3 in this case. Then there will be initialization of the application SBL, which is U-boot, and then the HLOS, high-level operating system, which is Android. This is just arbitrary lingo, so generic lingo, not arbitrary, generic lingo in order to accommodate for different solutions that this SoC may support. Well, you may need to start, usually we start from looking at a serial. Sometimes you have nice, convenient pads and so on. Some other times we didn't have them in our device. So we had to find out these small pads. Nothing really groundbreaking for this kind of audience. And we just see that there is no kernel printout. This is starting kernel is the only thing which is printed. I didn't cut the output. This is what you get if you connect the serial, nothing really more. No use of shell, even if you have serial. Nothing really. So what do we know now? That the PBL, so primary bootloader in Qualcomm lingo, the ROM is starting, is executing the SBL in EL3, so it's a secondary bootloader, which then arguably, well, we know from the documentation, will start something on the secure side, and also will start after that, you will start U-boot on the non-secure side. Nothing really groundbreaking, I would say. So, but that's what we know from our serial, and that's what we have. We don't have control on anything at this moment. We need to get the firmware. And this, as people that have played with the Google Nest Wi-Fi Pro, it's not that immediate, actually. The eMMC chip is located there in nearby the Qualcomm SoC. If you do an initial a quick probing, you may not find anything immediately and so on. I mean, at least in our quick probing, signals were not appearing, let's say, immediately. Usually you have this is found, right? Sometimes it's not that easy, but you're just a chip off away from tracing everything, which is actually what we did. We removed the chip and we did a full signal tracing on the PCB, and we just identified then the signal out of the BGA balls of the eMMC. Again, something which is a normal practice here. We try to dump it. We want to dump it in situ. So we connect to this without removing the chip, just because, we found it more convenient for us. We use, it was also cooler. We liked it. Low voltage eMMC adapter connected directly to an SD card reader in its support 1-bit mode. And that's the mode that you see in the picture. Unfortunately, this didn't work. We did further, and we identified the likely cause of this is that the clock signal was likely interfering with our process. There is no external crystal, so very likely the SoC was providing this clock signal. So a little more digging, we found the resistor and we found the pad, and we found this clock signal, removed the resistor, and then basically works. So we have been able to connect the eMMC directly to our, we removed the resistor and we were able to read out the eMMC. Actually, not even read out the eMMC. We're able to connect the eMMC on the board directly on our laptop through, basically, without even removing that. You know, it's pretty convenient if you can actually do that. And that's why we want to do, I don't want to read and write every time and do every time chip off and back. This is not something we want to do. Also, it's pretty annoying to solder BJ. It's doable. I mean, it's not, but it's annoying, right? So if you can do just like with a wire, in the end, it was just a matter of finding this clock signal and removing the capacitor. So we have been able to mount the eMMC on the board directly in our Linux environment. You see that is recognized as SDA, and there are basically 19 different partitions. So the notable partitions you see are the SBL, which is the secondary bootloader that we were seeing, the QSE A and B, because this is a device which does boot A and boot B. So in order to have always a copy that should be in principle functioning, and then there is U-boot A, U-boot B. Just two different copies that are used in an alternate way during an update. Okay. We just dumped them all just because, I mean, once you're here, it's pretty convenient. In order to make our life easier, we didn't remove the chip. We left it as it is, basically, and we just soldered headers for the serials, for the MMC. And in order for that resistor, we just use a jumper. So by removing the jumper, by connecting the jumper, we put just basically a 0 ohm resistor or an equivalent and remove. So this becomes pretty easy to access the MMC without even removing that. And that was, pretty convenient for us in the end. This allows to conveniently read and write by connecting to those headers and just removing a jumper or not. So it's like altering your PCB for convenience. So nothing really special and groundbreaking, just a convenient way of doing things, bypassing secure boot. It turns out that secure boot is enabled. How do you know? Well, you need to modify something for which you don't have the private key, of course, and make sure that this device fails. Indeed, we find that secure boot is enabled by Fuse because PBL verifies the SBL verifies U-boot verifies the kernel. We have tested all these options by modifying one bit in Flash, basically, and see that the boot process halted at the right moment. And you can see, for example, in this case, that by modifying the kernel partition, U-boot would say, hey, image authentication of a kernel is failing. So this actually proves, indeed, that there is a secure boot process that for sure verifies the chain until the kernel. And that's what we have to bypass, basically, in order to progress with our attack. There is this nice CV, which is, I think, Sergey knows pretty well. And we found it. We also found it. Basically, we didn't know that the CV would have been assigned. We already worked on this, but I mean, credits goes to Sergey, and we are applying basically using the same vulnerability. The U-boot searches for the partition apps BL-EMF, but it doesn't exist. Now, because it doesn't exist, I mean, it just says, hey, I'm missing a partition, and it's fine, it still continues, but at boot, it will print something, okay? This means, though, that you can create this partition yourself. So what we did is take the crash partition, resize it to make a little bit more space, and then we create a partition which is called with this name, because it's really the name that identifies the partition in the search. But this means that this app SBL-EMF also provides the environment variables to U-boot. Now, long story short, we have been able, by supplying environment variables, to bypass the check that is done by U-boot. So that if you would like to go a little bit more in details, there is a variable that says that is used for performing the secure authentication of the kernel. If you replace that variable and make it null, it's gone. So the authentication is basically gone. And we are able also to supply our own U-boot environment. So long story short, we achieved the same as has been done by Sergey. We achieved code execution in U-boot and also the bypass. Well, actually, not so much code execution. We really bypassed directly the kernel authentication because that's what we wanted. Now, it turns out that is not the kernel which is really authenticated, is the boot image. And the boot image authenticates the kernel, the RAM disk, but also the boot args for the kernel. So this means we can change all of them. We just need to repack a boot image, and this will be able to boot. We can boot it unsigned. We don't need a signature. So this means that we can change several things. For example, we can pass our boot args for saying that the console variable, which is which is passed to the kernel, is empty, and that's the reason why the kernel doesn't print. So what we did is replace that console variable, this one here, with another variable name. In this case, was realize. So if you replace a console equal null to equal nothing to realize equal nothing, console is still not assigned, and this means that the kernel will start printing. So it was really as simple as this. How do we get root? We modify the RAM disk in init.rc, and which is part of boot image, in order to start a root shell as part of the boot process. So we repack the boot image. We need to fix a CRC. We need to fix a few checksum. We just flash it. Long story short, we get a root shell with secure boot. In order to verify a few property of the device that we are Android, we use a get prop, and this is what you see in our device. Now, was just to get on the device in order to get a shell, because we would like to get EL3. Now, we are root, basically. What we have control here is only the user space on the non-secure side, EL0. Now, while root is pretty powerful, it's not as powerful as this guy in the TE side, okay? So this means that if you become EL3, you have full control on everything on the device, including on the secure side. That's basically our goal. How do we get there? Well, we have a plan. We could glitch a request to the monitor in order to achieve, potentially, if it's there, a read and write primitive in EL3 memory. Also, we like EMFI. I mean, to be fair, in our history, we have glitched with the clock voltage, with the laser, with EM. I mean, and it's a matter of preference. We like EMFI, and the reason is that we mostly don't need to modify the target. This means that I don't need to mess up with phrases or mess up with voltage. So if you have that capability, we usually go with that first. And then we explore more if it's needed. So if we are able to gain this read and write primitive, we would like to also bypass the TE memory protection in order to expand our control up to the point of achieving code execution in EL3. That's our final goal. So glitching an SMC request to EMFI, is that even possible? What do you think? Well, we did it. we did it already in 2021 in our research for the IPQ 4018. It was already done, but it was a really different purpose in that case. Now we are building an attack more structure on this case. So, but this requires that you've been able to send SMC to the TE. Now you cannot send an SMC from user space. The only privileged component that can send SMCs to the RE are EL1, both on the non-secure and the secure side. So the OS can send an SMC to the monitor, even QSE, and EL2, so the hypervisor on the RE side. So those are the only ones. So we need to get there, that we are able to send an SMC. We are still root, so EL0, user space. We don't have that capability yet. We need to build an MFI setup. We need to characterize the SoC and identify faults that would allow us to, in the end, to glitch this SMC. Okay, beautiful. Now, we need to get to the capability of doing EMFI. The first one, we need to acquire EL1 privilege. We need to become kernel. We need to have that ability. Well, we are root, so, and on the Nest, on the Wi-Fi Pro, it's pretty easy and convenient in a way, because there is devmem, which you can pack as part of the BusyBox. I don't even remember if it's part of the distribution. I'm not even sure, but you can put it in any way in your BusyBox and compile it, which allows us to read and write arbitrary memory addresses directly from user space. This requires root privileges, of course, but we are already root, so there's nothing stopping us from doing that. This is read and write. If you want just exec, we can build a custom Linux kernel module. It is possible to load a Linux kernel, an LKM on the Wi-Fi Pro. You just need to make sure that this is actually enabled in an ETRC, init.rc. So you need to ensure that this capability is there and does not get removed. We do this as part of research. We created a couple of LKMs, and you will see them in our presentation. We need to also to build a fault injection setup. Once we have an LKM that can send SMCs, we think we have that capability, we start thinking about the fault injection setup. Some ingredients are typically needed, regardless if you're doing voltage, clock, EM, laser. You still need some ingredients. These are communication. Usually you need to have a way of communicating with the target. We're communicating, meaning also even just listening. Sometimes you do fault injection by listening to power traces in order to detect if you're successful or not, depending on the shape that you get. You can even get through side channels in order to guide your fault injection process. It's possible, and we have done it. But in this case, we have the ability to talk through a serial port. We don't need to go to that extent. For sure, you need to have a way of detecting that you are successful, and you need to have a way of triggering the process that you want to glitch. This is always needed. We would like to receive some kind of information, well, it is called usually a trigger, that tells us when is the right time to glitch. And we also would like to reset the device, because in order to make sure that it reboots in a known state. Because if you fault the device and you don't see the effect, that device may be in a faulty state, and you fault on top, and you fault on top, and you fault on top. You may enter into states which can be useful, but are very difficult to decode, understand, and reproduce. So this means that, for example, what we do is that every time we fault the device or reset or do something to the device, we don't receive the regular response, we reset. Always. In a way that we are always targeting and glitching a known good state to a possible bad state, so that this can be reproduced to a certain extent. Communication, we have a serial port, and we have even soldered headers. This is straightforward. So this is always possible to be done in this case, at least. We need a trigger. Well, for triggering, we would like to have something that informs us, hey, look, this process that you want to glitch is starting, and this process that you want to glitch is ending. So it gives us a time window and gives us a reference. Ideally, if you are characterizing a target and you have this luxury, you would like to control a GPIO pin. Raise it up before you start your attack and put it down after your attack, your process finishes. We don't have many options, but there is one, the factory reset button that is on the target. There is no actual reset. That is a button, is a GPIO, and is exposed on the, in EL3. This is exposed as an input. Why? Because you need to press the button in order to reset it, right? So what we have been doing is that we learned our way to set this GPIO as an output rather than as an input. So this means that what you see there are the lines that are needed for configuring that GPIO, the 487, as an output. So this is totally fine. So this means that if we are able to find the right memory location to write, so to make this output go up and go down, well, we are in business, right? Now, it turns out that we would like to control this pin directly. We can always do through the driver, hey, I want to do factory reset or fix it, but this is inconvenient for timing, and this is inconvenient for flexibility. In the end, if you want to do an SMC from the kernel, we would like to do this from the kernel, and it's not that convenient to go to your user space driver and do this for me, right? So we want to have addresses and live addresses. So we just probe the GPIO address space with devmem. So we just write 1, 1, 1, 1, 1, 1, 0, 1, 0, of course, until we see a toggling on the spin. And that's how we brute force and we find the right address for this guy. This is a simple technique, but it works in general. We have been using not only now, of course. It turns out that we found the address 01016004. And if you write, let's say, the first command, so 32 masked with 03. 03 means we are raising the pin high. And the same address, we write 0, and we are putting the GPIO pin low. So this means that before we start any operation, we raise the spin, and then we have the target we want to glitch, and we go down. So this gives us a very good time reference. The trigger signal now becomes easily accessible. You just need to make a soldering and use headers like there's no tomorrow. I mean, because it's just convenient. And we just need the last signal, which is reset, right? Now, it turns out there is no reset button. There is no reset signal easily accessible. So basically, we go the usual older way of unplugging the cable. But unplugging the cable manually in a fault injection campaign is a totally terrible idea. And that's why we use a solid state relay in order to power cycle our target. So this means that we can send, let's say, raise a pin, let's say, to reset the target by using this solid state relay, which will cut the power and we'll bring it back whenever we want. So this allows us to automate any process that we actually need for the glitching. The glitching is done with the best equipment that we have available, we have access to, is from Riscure Keysight. And we use the EMFI transient probe to generate the EM impulse. We use the spider as an FPGA for synchronizing the glitch, and also the EM probe station, such as that we can move the stage. Now, keep in mind that this solution is slightly different from the usual ones where the probe is fixed and the table moves with the target. In this solution, the table is fixed and the EMFI probe moves in a X, Y, and Z axis. No, don't suspend. So that's not the right moment. So our setup looks like this, and what we find is that our target is basically there. So let me do this so you can see our target is on an S-Wi-Fi probe. Oops, sorry. This is the one. We communicate with a UART through a USB to UART converter. We use an oscilloscope for measuring traces of what we see, so power traces and other things we're going to see in a moment. We are going to use the relay power supply, which is controlled directly by the spider. So from the spider, we can say reset the target or not. And basically, we do everything through the spider. The spider will reset according to our script. The spider will just trigger the glitch on the EMFI probe, which has been positioned at a specific specific location. Now, all of this is actually automated and scripted. We usually have campaigns that go on for days and weeks unattended. And in the meantime that we collect data, we also have analyzers that collect the data that we get back. So everything is fully automated, and it's all machine time, and the analyst time actually is doing something else in his own life and coming back to check results with the data analyzer and visualizer. You will see them in a moment. So we start the characterization with all this, with this target for the Qualcomm SoC. And this allows to check if the SoC is vulnerable. What does vulnerable mean at all? Vulnerable means that I have a technique of fault injection that is able to affect the behavior of the target. Now, this is a vulnerability, technically speaking, because it shouldn't be able to affect the behavior of the target. Now, like in software, a vulnerability does not necessarily mean it's exploitable. And then some vulnerability may be exploitable for some purposes, but not for other purposes, right? So this terminology, if you think about it, fully checks for fault injection. The SoC is vulnerable if you can affect it. If you can affect it in a way that you can use it, then the vulnerability is exploitable. Now, the vulnerability may be allowed to exploit some specific and reach some specific goal, but not others, because this will depend on the surrounding condition. This totally matches with the software terminology. If you think about vulnerability as being able to affect the target and exploitability as being able to use that fault for reaching a goal. So this is actually, using this terminology facilitates the life of software people, hardware people, and anybody in between. Let's start using, if you don't mind. That's what we mean. We also identify parameters like glitch location, X and Y, and power that are able to trigger some specific effect that we prefer. We are going to see them in a moment. What do we do in this characterization? In our Linux kernel module, we run code. Now, we assume that if we are able to glitch that code running in the kernel, this means that we are also able to affect the QSCE code. That's basically our assumption. This is reasonable because maybe someone does not know that when you do an SMC on one core, you are running the TE code on the same core. There is no reason why this core should be vulnerable when running RE, but not when running TE code. It's the same single core and CPU. Any SMC is serviced on the T side on the same core that does the request. So there is no change. So if you are able to glitch the core while running RE code, there is a very high likelihood that is also the same core is vulnerable when running TE code. Which kind of code do we run? Nothing really groundbreaking, but we do something a bit optimizing from the usual counter loop. So you may see that you have counter loops that count from 0 to something. Okay, we have optimized a little thing in our 15 years of testing. We are not the only one, of course. There are many people that do like this. This is an addition. You see this X. This is a macro that is going to add. So you initialize 0 into R7, and then you add 1 10,000 times. This is really compact way of writing X, because this will be expanded to this, will be expanded to this, and so on. And that's one letter that means I'm adding 10 times 1 to that register. Why we don't have a loop? We don't have a loop because if you are counting, this already involves 2 instructions, adding and going back. So an add and a branch, an add and a branch. And it becomes more difficult to interpret the outcome. We like to have one single instruction in entire unrolled loop so that we can refer what's happening more easily to what we are glitching. So glitching a single instruction in the loop allows us to better decode what we see. Our trigger is raised up before the counting as put down after. At the end, we just print the value of counter, which is the value in R7. R7 goes in counter, and then we print it. So we should see A, then 10,000 in X, which is 2710, B, 2710, C. That's what we should be seeing at the end in a normal situation. And this is what we do when we are simply loading the kernel, the LKM. That's what happens. It just counts, nothing more. So we want to do a couple of tricks. We want to make sure that if we have to reset, this reset needs to be as fast as possible. Speed is everything in fault injection. The fastest you are, the more parameters you explore. Now, that's why we decide to start the shell very early. For example, in ERC or even in RAM disk, if you can, to reduce the reboot time penalty. And we also turn off any other core except one in order to avoid execution of concurrent code. These are small tricks which allows us to have repeatability for characterization. This is the attack windows in terms of time. When you do an SMC, you are calling an SMC from the kernel. So this is basically RE time. Then this is processing on the QSC side. And then this is the response in the RE side. We can only see, this is where we put the trigger up and put the trigger down, but we cannot easily target this part, not because we are outside of the RE side, on the RE side. The parameter we are using, we are scanning this with a 10 by 10 grid. Well, I mean, we can object how fine is that, but our result says that we are good. We do just 45 attempts per location, and we just go around a few times. The time window here of the attack is in the order of 60 microseconds, okay? So we decide to be on the safe side to glitch between 10 and 20 milliseconds. No, microsecond. No, this is wrong. I need to fix it. And we just use between 0 and 100% of our probe power and see basically what happens. Like I said, we like to visualize data and parameters. We do see that there are some area where we find some different counter on the chip. Okay. Now, checking time. We do see counter where the instruction is skipped. Or we do see that sometimes the counter is above 2710. Now, long story short, this can be only explained by corrupting the instruction. So this means we have locations which are good, and we decide to put our location, our probe in one of those locations. And the location that we choose is where we have the instruction skipping. We are going to see why shortly. So we have identified parameters. We know where to put our probe. We know where the timing that we would have on SMC. So we are good to go to skip some instruction, but we need to see which one. Now, it's nice to use instruction skipping fault model for skipping conditional checks, call to function, because you would skip the function call, you would skip the checks itself. What can we target? We dump, we reverse, we extract the QSC partition, we identify all the SMC handlers, and we try to find some that could be suitable for us. Now, a little bit of code. There are two which are relevant, which allows to read and write. And yes, read and write. And this will happen through read from and write to. These are two functions. It turns out that these two functions will write what is passed in X2 and X2. Here in X2 and X3 is written, and you will read what passed in X2. Unfortunately, there is a check. You cannot read everything. You can read what is passed by is allowed address. Now, is allowed address is a check which is in there. What does it do? It checks that the address that you pass belongs to a whitelist. You can only read and write through that whitelist, okay? Now, there are 8 regions that are whitelisted. There is a very specific address that you can read and write from. So this means that we cannot do more than that, unless we glitch this check. So if we glitch is allowed address and we pass an invalid address, we may be able to read and write from it. Okay. Now there is more information if you want to replicate this attack in the slides. I'm just explaining how we proceeded. So we create an LKM that allows sending arbitrary SMCs, specifically these two, and we would like to have a glitch that allows us to read and write to arbitrary region. So this means we need to call this function and glitch them. There is a little bit of an annoyance that if you read for one of them, if you read from an allowed location, you actually get the result out with IO access read. If you read a non-whitelist location, you get 0. So these two cases are perfectly distinguishable. You can check them, right? This is the timing. There is a little bit of jitter there, but I mean, that we need to overcome, require some thinking. So basically, what do? We try to read the access, the start of your monitor. This is not allowed. We should not be able to read it. But if we glitch successfully, this is what we should be reading back in practice. So if we get this number back, it means that we have been successful in glitching. The attack window is 5 microseconds. We apply the same parameters as before, and it turns out that you see some purple over here where we are successful. Now we have one successful glitch every 1 hour and 40. As at start, but we have improved quite a little bit in parameters, so we end up into one successful glitch, so we can read arbitrary memory every 12 minutes. That's basically. We have an arbitrary memory read. Same story for the write analysis. Unfortunately, the two cases, so if we are able to write a whitelisted address or the non-whitelisted address, we cannot easily distinguish. So the only thing that we can do is that we write some location that we can read after. So RE memory is not allowed by this call, right? So this means that we can glitch a write to a RE memory and read it from RE. Basically, this allows to tune our parameters, and we found out that we are successful. So we glitch in this location, an RE address, and we read back from RE user space. That's really good in terms of reading the memory back. Indeed, we are successful every 10 minutes. This allows to choose parameter where we can write everywhere in memory. So instead of writing to an RE address, we can write to a TE now, because we know which are the parameters that will work for us, okay? We have an arbitrary EL3 memory write. Now, if you need to write a shellcode this way, it's really inconvenient, right? You need to write 32 bits like this, and this doesn't work. So the question is that, can you defeat a TE with a single write? Can you kill it? Because that's the whole point, right? Because if you could do it. Well, it turns out that if you look into the hardware of Qualcomm XPUs, which are Frustum are the space controller, which are in charge of blocking everything, they have a configuration which goes into registers, okay? Now, these registers are writable, so if we use our write for writing those registers, we will change the configuration. Yes, they are address space controller. They filter all the requests which comes from non-secure memory, and they need to be configured at boot. The table of configuration is somewhere in memory. It turns out that if you try to access TE memory from RE, this is the exception that you get. If you go look into the TZ log file, you will get more. So you will get to know more. This is an example. And you see that the first entry, it dumped the entire configuration, all the XPU is dumped. And the first entry covers exactly the secure monitor. So if we change that configuration in the register, we would be able to unprotect the secure monitor memory. There may be multiple XPU. You need to understand which one. And the configuration that you have just seen must be there in EL3. And this configuration needs to be applied to the actual register. We reverse, we try to find the base address, and it turns out that by reversing, we find that the XPU register, the hardware, starts at 6E000. Now, by using great research from Quartz Lab, we find the layout we confirm that the layout they found out is also for us, valid for us. So we know where are the start and end address of every region in the register. So this means that we can tune our glitch such as that we can write that register to unprotect the secure monitor. This is basically our intent. We just need to make a glitch that writes at 6E250. This is the math that goes through all the base addresses for whoever wants to go through that. So the attack is that we write at that address with our primitive. This means that our XPU will not protect the secure monitor anymore, or not as much as we want. And this means that that monitor becomes accessible now by the RE memory also. Because the only thing that blocks RE request to secure memory are these XPUs, not the MMUs. We can discuss that at later if you've the doubt. So basically, we set a value in this register that shrinks the value of secure memory. If this works, we are able to access the monitor from RE, basically from user space, which is great, actually. We glitch this address. We change the value of the monitor that is in the register from this is the start of the monitor to this other address, which is a bit after. So we gain some space, which becomes accessible in the monitor. We glitch, and we verify that we are successful just by trying to read and write the secure monitor memory. Again, long story short, we are successful every 37 minutes. So this means that we remove the protection on the XPU once and for all, and this stays there until the next reboot. So once we have one successful glitch, we can read and write the monitor from RE. It turns out the TE continue executing as intended, because it does not even know that the protection has been removed. So nothing is really can be detected from the TE side. But the RE can now access, so the kernel can now access this memory area. We can do from user space because we have devmem, which writes and reads physical memory. So what we have done now is that we have full control of the root of the kernel and now of the secure monitor. So we can read and write. Long story short, we can write from RE. And basically, we would like to have a more convenient way of writing and reading, right? So basically, we can patch the code of this read and write in order to remove the protection. We patch it out. The checks are removed, and this is what we need to patch in the IO is allowed address. We patch this to return always 1. So this means that the allowed address says, hey, this is good. This address is always good. So, long story short, we can now write and read from devmem from user space. We can patch directly using devmem. My apologies. And now we can use a IO access read to read the start of the secure monitor, which is intended like this. So this brings us an arbitrary read and write with EMFI glitching. And we have done this by changing the XPU. Now everything is trivial now. We can write our own shellcode in a secure monitor. We issue an SMC that calls this shellcode. And then we prove that we are running in EL3 by reading the register TTBR0 EL3, because it can be read only by EL3 privileges. Basically we do a request, we trigger our shellcode, and indeed we do see that, The output is 4A C0 F000. This output is meaningful because TTPR0 contains the base address of the MMU page table. And this is indeed insecure memory. So we actually proven that we got arbitrary code execution. So basically, conclusion, the SoC is vulnerable to EMFI. Physical access is required. This monitor code is not hardened against fault injection. Again, not surprising. The surprising part may be that you could have locked the register of the XPU because it's a feature you can do. At least we think it's possible for these XPUs because some others can be done. This would have prevented us from changing the value. There are several mitigations that can be applied. You can prevent the injection with the shield. You can detect with a sensor. You can address at the fault level by using parity, check buses, register in memory, and so on. So basically introducing redundancy because that's one of the most used countermeasures of fault injection. And for exploit, you prevent us from changing the XPU. You can have checksums in the configuration so we can override it. So there are several things that can be done. And I would invite you to think using this model because it allows to address what is the technique that you use for generating the glitch separately from the impact that you have with the fault. Keep in mind that the fault is just changing one instruction, and this can happen with any technique. So this means that any mitigation that you have here on this side will actually work for any technique. I hope this was interesting for you. Fault injection can be very powerful if combined with software exploit, especially if you know your system well. We use fault injection for compromising TEs in our daily work, basically. And the TE can be defeated by a single write. For who actually knows a TE pretty well, this is not really news, but let's see in practice. Characterization, and we got EL3. That's basically it. Thank you, and sorry for a little bit of the
Thank you for your talk. We're a bit over time, but let's do one question.
So I missed a little context, or I didn't understand quite. Once you had successfully faulted the instruction so that you could do an arbitrary read, I was expecting you to turn around and immediately patch that instruction so you didn't have to fault it again. But instead you went off and changed the XPUs, and then you came back later on and you changed the instructions so that you still had the arbitrary read. Why did you do the XPU?
So, do I say it correctly? Say, why after changing the XPUs you've not used DevMem? Is this what you're asking?
No, it's more, why did you bother changing the XPUs instead of using your faulting in order to just change it so you didn't need to use faulting anymore to do the arbitrary write? Because
the code section is not writable because MMU. And we bypass the MMU configuration from the RE side because, of course, the REC that doesn't care about the MMU setting of the TE.
Sure. All right, cool. Thank you.
All right. Cristofaro will be around for more questions later. Let's thank the speaker again.
Thank you.